Hello, welcome back to Act 1 of Hi Jax. This is Lecture 2, High Procedural Random Number Generation. This is Lecture 2 out of 5 in the first act, which is our section on the basic elements of Jax programming as a paradigm, and the kind of things you need to do to code array programs in Jax. And today we're going to be looking at implementing a classical perceptron, which is one of the first neural network architectures ever invented. And we're going to be doing it using the historical technique from the Perceptron paper of stochastic gradient descent on one random sample at a time. This is going to give us a perfect opportunity to explore Jax's tools for random number generation. And they're a little bit quirky compared to other frameworks like NumPy or PyTorch because of Jax's immutability requirement. And so we're going to see how, the common patterns for using Jax to work around that requirement and have immutable random number generators that can still give procedurally generated random numbers. And we'll also be able to explore and revise some of the other things we've been learning about in this lecture. So let's get started. So I'm here in the HiJax repository once again with the HiJax virtual environment, and I'm going to CD straight into the lecture 02 folder. So inside this folder, I have my script Perceptrons, perceptron.py, and so I'm going to go into this script and show you around. Once again, we've got some imports, the classic things, time, pyro, matplotlib, and jax typing, plus all we need for jax, so jax and jax.numpy. And we've got an empty main function that's going to be taking a dataset size, learning rate, and a random seed this time because we're going to need to initialize our random number generator using this seed. And then the rest of this script is already filled in. It's some visualization code using matplotlib. This is not the focus of the tutorial, so I'm not going to go through that. You can follow along by copying this empty file from the HiJax repository on GitHub. Let's get straight into implementing our first taste of random number generation in Jax. If we want to train a classical perceptron, we're going to need some data. And so I basically want to generate two data sets or two sort of sets of points in, let's just do 2 dimensions. And they're going to be like 2 Gaussian sort of clusters in 2 dimensions. And so in order to implement that, I just need to use jax.random, which is the submodule that we're going to be using today. I'm just looking up the parameters that I used for the data. And let's get started. So before we do any random number generation, we need to initialize the PRNG, the procedural random number generator. And so to do that, we do this with the jax.random module, which has this function key that takes a seed as input. And we're going to give it our input seed, which is configurable by the command line with Tyro. And this will give us back our random number state, which is common to call key in Jax. And that's all we need to do to initialize it. But then to use it, we're going to need to do something else. So now the next thing I want to do is actually draw some of this randomness from the PRNG and use this to initialize a data set. So basically, jax.random is the library that has everything to do with PRNG state management and also generating random numbers of different types. And so before we talk about state management, I want to show you the kind of thing we can do to generate some actual random data. So that's going to look like, if we want this sort of Gaussian cloud for the positive examples, which I'm going to call xpos, then I'm going to call jax.random.multivariate normal, which is the function I found in the documentation. Just looking on the Jax website, it has all of the functions here that you have for different types of distributions, and multivariate normal is the one that meets what I want for this. And so the parameters of this multivariate normal are it takes a key, which is the sort of random state, and we're going to give it our key. And then it takes a mean for the random normal, and I want to give it this, I want this section of the data to be focused around the point 1, 1. So I'm just going to use JNP1s and give it length 2 to get that point 1, 1. And then it wants a covariance. And so a covariance is a matrix. It's a 2x2 matrix because we're in 2D. And so I just want to use, I want this to be isotropic I want to use the identity matrix, but I don't want it to be a standard normal distribution. I want it to be a little bit tighter. So I'm going to just 0.25 times JNPI, which will give us the two-dimensional identity matrix. And then I think that's all. Oh, no, I need to say how many points I want. So this is going to give me, by default, this would give me a single pair, a single like two-dimensional array. I actually want a bunch of points. I want num points divided by 2, and this will then give me, where if I want 256 points, this is going to give me 128 points that are going to be positive examples for classification. And so I better make sure this is a tuple so that it can be a shape. This is now going to give me a 128 by 2 array as the output of this thing. And yeah, so let me now explain how to actually do this. If we do this, actually, I think it would work, and I could print out the shape to show that. I think this would work. So we haven't done anything special for state management, but let me just go ahead and call this and see what happens. Oh, it's actually, I didn't print out the shape, I printed out the array, but you can see the point. This is a random 128 by 2 matrix that it's given us out. So that's great. And these are randomly distributed with a mean of 1, 1. I know that you can see that from just looking at them like this. But anyway, now let's talk about state management. So the thing is, this is a pure function because it's a jax function. Jax functions are pure. And what that means is, if I was to sort of go on to use this key, this random state, I haven't actually changed this key variable because that can't be mutated inside a function. And by the way, anyway, jax arrays are immutable, so you can't actually change this. And there was nowhere where I returned a new state that would be like an updated version of this. And this is sort of the key principle behind the jax.random library and state management is that you have to manually say when you want to mutate the state. And you do that with this sort of forking paradigm. So we're going to do this instead. Instead of passing in our random state, we're going to take our random state and split it in 2. And get sort of one part that is going to be used for this computation and another part that is going to be used for any future computation. And so the typical paradigm or like pattern of doing this is to say, make a new key called, let's say, key pos, because it's for my positive data. And then I'll have a second key. I'll just call this key 2 for now. And this is going to be jax.random.split of the original key. Now this will give us, if I put key pos in here, this will give us sort of different numbers out. I could verify that the last one here is 0.6, 0.9, and if I save this and run it, I should get something different, most likely. Yeah, that looks different to me. And so this has given us not the original random state used to generate these numbers, but we've used some other state. And crucially, we've got this key 2, which we can then keep using in the code the next time we need random numbers. However, it's common to just call that key and then it will override the old state. And that also means that we can't then reuse this state and split it accidentally because anytime we reference key from now on, it's going to be this sort of second version of the state. And so this is sort of the pattern that you have in JAX when you want something random, is you need to take a key and split it in pieces and then use some of the pieces to generate random numbers, and the rest of the pieces you thread them through the rest of your program and you use those to generate future random numbers. And all the way, there was no actual mutation involved, there was only overwriting. And so that is how JAX random number generation happens, even though all of the variables involved are immutable. Now, this paradigm for generating random numbers also has some other advantages. It sort of works well with composition and like breaking your function up into like helper functions, and any changes that you make to the sequence of random numbers that you generate later in one function don't have to affect the random numbers that you would draw in the future. So it can be easier to get like modular deterministic behavior in complex training code, and that could be one advantage of this way. One disadvantage is that there's like more steps involved to generating random numbers, and so it's just something you kind of have to get used to. However, anyway, that's our first look at random number generation. Let's do a little bit more practice with this and also finish writing our code that is going to generate our data. And so to do this, instead of printing out this data, what I want to do is generate some labels. And so I'm going to use Y's to be the sort of array that stores my labels. And all of these positive examples are going to have the label 1. So I just want to use JNP1s to generate this. And then I want to make sure there are enough of these. So it should be num points over 2. And I don't want these to be floating point ones, which it will be by default. So I'm going to say that the D type, if I could spell, should be bool. So this will give me an array of points, and this will give me an array of 128 trues, JNP1s, because 1 for booleans is true. And so this is the positive part of my data set. Now I'm going to basically repeat the same thing. In fact, I want to repeat the same thing, so I'm just going to copy this code and do it again, but I'm going to say this is key neg and x is neg, and it will be the same multivariate but normal command with a new key. I'm going to be using key neg here instead of key pos. And so if you have a look, we've got this key. We first split off key pos, and then we keep this half of the tree for future things. We split this key again to get key neg, and we use that to generate the multivariate but normal data for the negative examples. And so you're starting to see this sort of tree of random number states, random number generator states in practice. Anyway, we don't want these to have the mean of 1, 1 anymore. We want these to be sort of separable from those. So we want to have the mean of 0, 0, and so that would be JNP 0s 2. They can have the same covariance though, so the sort of similar tightly clustered cloud around there. And then the labels for these will be y neg, and instead of 1s, we also want Boolean 0s, which is going to be an array of 128 falses. So this should all run now. And except I'm not putting any output, so it's not interesting. I'm going to do some output soon. But first I need to just combine this training data into an x's array and a y's array. And so to do that, this is another chance to use our concatenate function from the NumPy, from jax.NumPy. And so I'm going to take x's pos and x's neg and combine those along axis 0 to become a single 256 length by 2 array of x's, which is going to be our examples. And we'll do the same for y. So jnp.concatenate y's pos and y's neg along axis 0, which is the only axis in this case. And this is going to give me a single 256 long Boolean array of labels. Now, the last thing we need to do before we train with this data is shuffle it. At the moment, we're using concatenate, so all of the positive examples come before all of the negative examples. And if we train in that order, I don't think it's going to learn very well. So instead, let's shuffle it up so that it's sort of, on average, seeing positive and negative examples kind of together. And so this is another random operation to shuffle. And so we're going to need another use of the jax.random API. And the function that we're going to want to use is jax.random.permutation. I guess I can look that up in the API reference here. It returns a randomly permuted array or range. I'm going to want a range so I can do some indexing. Because I want to call another random operation, I'm going to need another key. So let's call this key shuffle. And I'm going to split that off from the key, jax.random.split. You type this out a million times, jax.random.split over and over again when you're writing JAX code. Let's get our permutation, our shuffling indices, and call it pi for permutation. And then we'll say jax.random.permutation, which, let's see, it takes a key and a array, or this array is allowed to be just an integer if you look up in the documentation. So we want to use key shuffle, and we want to use x equals, I could use the num points, but if num points is odd, then that actually won't be the right number. So let me just use y size, because then, for example, if this was 257, we would have halved it to 128 twice, and we'd have 256 by the end, and y's will have size 256. This is going to give me basically a shuffling of a range 256. Which I'm going to then be able to use as an index, and I'll say x's shuffled, or x's, is equal to x's with this indexing, and that's going to implement the permutation. And same with y's. And so now I have shuffled my data, so I better say that's what I was doing here. So we initialized the data set, and then we shuffled the data. Okay, so the next step is going to be to, I have prepared, before we move on to training the model, I have prepared a viz data function, and let's try this now to see what we've built. I like to make things really visual in this course, so let's print out the viz data. I'm using print because this is going to return a matplotlib libplot, which you need to print to get it on the terminal. So viz data takes x's and y's, And I guess I could have done this before or after shuffling it. Maybe it makes actually slightly more sense to do it before, but it actually isn't going to make a difference to the visualization because the scatter plot isn't going to depend on the order of the data points. But then I can run the code, and now we'll see something kind of satisfying. We have our two clusters, and I'm just realizing that I thought these were going to be separated, and I've plotted from -3 to 3. I think I've made a mistake, and what I really wanted was to have these not have zeros as the mean, but ones and then minus. So they have like -1, -1. And this should be much, not ones. This should be more separated. Yeah, indeed. This is what I was expecting. So good thing we did that. We did this visualization so we could see what our data was looking like. Okay, so I've got two axes now. I've got the x0 axis and the x1 axis. Rather than calling them x and y, like you might sometimes do, I've called them x0 and x1 because they're sort of the two elements of the x's data, and the y's is going to be the label that the notation that I reserve for the actual label of the examples, which is like whether it's a positive example or a negative example. These ones are true and these ones are false. And so these are my ground truth labels, and you can see they're just linearly separable, it looks like. So we should be able to learn a classifier that learns a line that runs through here and will tell us on which side it is on, will sort of tell us which of these types of examples it is. And so that is what we're going to do next. And so now we've shuffled the data. Let's now define our model. So the classical perceptron is like one of the simplest neural networks you can imagine. You can actually think of it as basically a single neuron that has a bunch of inputs coming in scaled by weights, and then it makes a decision whether to fire or not. And that decision is kind of like the classification. And so in our case, we're going to be training a super simple model because not only is this only a single neuron, it actually also only has two inputs because it just has x0 and x1. So let me show you on the whiteboard what this model is going to do and what the parameters are. So behind me, I've drawn an example of the perceptron that we're going to be studying. And you can see that I've drawn one circle here to represent x0, the first input, and another circle to represent x1, the next input. These inputs are going to come in and go up to this neuron here, which is the perceptron itself. And this is going to be scaled by one weight, and this is going to be scaled by another weight. You could call them W0 and W1. And then up here, we're going to have the neuron. It's going to have a third weight, W2, that represents a bias. And then whether or not, depending on like what this neuron's sum of all of those inputs is going to be, the scaled x0, the scaled x1, and the bias added together, that's going to give us the logit, which is like a number representing the probability of a positive classification, but it's like in log space. And so the output of this we're going to call logit. And so just like before, in order to actually define this perceptron model, we're going to need two things. We're going to need to first define the actual weight vector and the actual parameter. And I thought it would be fun, last time we hard-coded it, I thought it'd be fun this time to randomly generate a parameter. And so we can do that. We can say key model init key is jax.random.split, because remember, we can't use key. We have to make a new sort of fork of the key and use that. And then I can randomly initialize this model as using jax.random.normal, and then the key can be key model init. And then I want the shape of this thing to be, I want three weights basically, because there's W0, W1, and W2, the bias. And so this will give me a floating point array of size 3, where all of the elements are standard normal. And that's a suitable initialization for today. And this will give me a random initial decision boundary for my problem. I think we could now show off what that decision boundary actually is, because we have this vis model function as well. And so if I have a look in my code at vis model, it's going to take a float array of size 3. That's what we just generated. X's is going to be our inputs, n and 2. So this is like the number of data points, and this is x0, x1. And then it's going to take a step as well, so it can label how far we are in training. And it's going to return an MP plot. So I might as well use that. let me go back to this part in the code. I might as well use vismodel, w, x's, and we'll set the step to 0. Why not? This is going to give me an MP plot. So let me just print that out, and then we're going to see what our model, what our current decision boundary looks like. Oh, of course, I didn't define the forward pass. I forgot. That's the other thing. It's not enough to just initialize the model. We also have to say what the computation is going to be. My apologies. So let's define forward for this model. It's going to take a weight, which is going to be this floating array. It's going to be this floating array of size 3, which is our parameters for our perceptron. It's going to take, we'll do a single data point this time, which is going to be a floating array of size 2. This is just a single x0, x1 pair. And then it's going to return this logit, which is going to be a single float. So in order to do this, the best way to do this is going to be to slice up our weight, get the first 2 elements and call those A. And so A is going to be a float 2 array. And then we'll take our bias as the third component. So sorry, not B, this should be W. And so this is going to be, we've got W0, W1, and W2. So this is W2 will be our bias. And then we can do the actual forward pass by taking the dot product between X and our array A, and then adding B. And so this will be a 2 vector times a 2 vector, scaling them and then adding them together in one operation. And then this B will be adding the bias. And this will be that sum of that neuron in the diagram. And that will be the output of our model. And so that's the forward pass. And now this code here depends on that forward operation. And so now it should actually work. And there we go. So we have the classifications according to our randomly initialized perceptron. And it looks like it thinks these points over here are cyan, so they're like class 1, and the rest are magenta. And so obviously this is not correct, but we're going to train the model and it's going to get better at that. So let's do this. So let's do the training loop. So for the training loop, what we need to do is go through all of the examples, feed each one into the model, and then use that to do a gradient descent step to update the model. But this is going to be stochastic gradient descent, and that is because we're not doing the full batch of data, we're just doing one at a time. Interestingly, you may have heard of stochastic gradient descent before, and it's often used to refer to what is actually better thought of as or sort of more technically should be called stochastic mini-batch gradient descent, if you want to be verbose, which refers to randomly choosing a subset of the data and putting all of that through the model in a batch or a mini-batch and doing an update based on that. And then if you were to do all of the data at once, that would be stochastic full batch gradient descent, where you have the entire data and you put it in a batch through the network. And what we're doing is stochastic gradient descent, which was originally used to mean just a single data point at once rather than and no batching at all. And so we're going to implement that. And so let me just make sure I'm not missing anything. Yeah, so we can visualize our model at step 1, and then we can go through the whole data. And so I want to keep track of like what the step number is for the visualization. But basically I want individual X's and Y's. And so I'm going to do this by enumerating the zip of the X's and Y's. So I'll get both of those together, and then I'll be getting pairs X, Y, and then I'll enumerate, so I'll also get an ID with those. And so this is going to be my for loop. And then, just like last time, I'm going to get a loss and a gradient by using the jax value and grad transformation on the loss function, which we haven't written yet, but we'll write in a moment. And the loss function is going to take w, x, and y, so the value and grad version of the loss function will also take that. And then I want to do my update. I want to say w is equal to w minus learning rate times g. So this is our gradient. We're scaling it by the learning rate and then using that to decrease, to move the parameters in a direction that most decreases the loss. And then I'm ready to plot again and go around the loop. So, but to do this, I want to make sure it's an animation. So I'm going to say the plot is going to be the viz model of what do we say the viz model takes. So viz model takes w, x's, and a step, and we actually have a step now. So we better put step in. And I just noticed that the visualization must be adding 1 for us. So this is going to enumerate starting from 0, and then it will be like how many steps it has been. And then I want to print the plot, but to make it an animation, I'm going to do the thing I did last time, where we use an ANSI escape code to make sure that we overwrite the last few lines. And actually before that, without typing out the ANSI escape code, which I remember last time I accidentally typed it wrong, I'm going to just use this trick from matplotlib, where if you just print out the negative of a plot, then it's going to overwrite the size of that plot. Go back that many lines before printing whatever comes next, which here is going to be the plot. And this isn't the last plot we wrote. This is the one we generated, but they're all the same size, and so this should work. And then I need to slow this down so that we can actually see it in motion. And this should work, except we haven't implemented this loss function. So that's the last thing we need to do. So let's define the loss function. So it's going to take as input the thing we want to differentiate with respect to. That's always the first argument, unless we were to use sort of custom parameters on our loss function, on our grad function. And in this case, we're taking the derivative with respect to the model. So let's have that first. And then it's going to take a single data point, which we said was an x and a y. And the x is a float array 2. And the y is actually a bool scalar. So it's a bool array, and to indicate a scalar, I just use an empty string in jax typing. And then the output of this is going to be a float. And so it's a single scalar representing, I could, just to make the point, I could equivalently have called this float array scalar, and I could have equivalently called this just bool, but it doesn't really matter what we call them, it's just for us. We're not using these types anywhere. Let's implement the actual loss function. So I need to do a forward pass through the model, so I need to get the logit, and that is going to be given by what we wrote before, this forward. And so we go forward of w on x. This will give us our logit, which logit is representing the log of a probability that it's class 1. And the loss function we want to use is cross-entropy loss for classification. And so I'm going to calculate the cross-entropy from a Dirac distribution, or a distribution that's concentrated on all of the probability on the true label. So if this is true, then it would be all of the probability on 1, and if it's false, then all of the probability would be on 0. And I want to take the cross-entropy with respect to that. And at one point I understood this when I wrote it, but I've forgotten exactly how it works. But you just need to make sure that you take the log add x of 0 and the logit. I think this is representing the fact that the logits are unnormalized, and so we kind of think of it as normalized. Think of it as relative to what the other prediction is, and let's just say the other prediction is 0. And then if this is positive, it's going to mean that we have like greater than 50% probability that the classification is 1. And if it's negative, as in less than 0, that's going to mean there's greater than 50% probability of the other direction, that the loss is, that the input is classified negative, classified 0. And so if you take this JNP log add x, it's going to do the appropriate transformation, and then the actual cross entropy part comes in when you also need to you would also need to normalize this. I should stop saying normalize. I don't think we're normalizing here. You need to take away if the true label is true, then the cross entropy is going to depend on the y value, and otherwise it's going to be 0. On that logit value, and otherwise it's going to be on 0. So we'll just multiply this boolean by the logit that we get. I think that's not like a super helpful explanation of what's going on here, but this is a very standard formula, and just make sure it looks like this, and then it's going to work. Very standard formula, I should say, for cross entropy when you're dealing with like one true label like this, represented as boolean, and one logit like this. But this is what all the frameworks would implement, like PyTorch or whatever would have a version of this function similarly. And this is just what it looks like. And so now that we've implemented that loss, this is the cross entropy. You could have some fun deriving that from first principles if you're not convinced. But for now, I think we're ready to run the code. So let's see if there are any errors. Indeed, there are. So step was not defined, and that's because I called this t. So sorry about that. And now we're learning. Okay, so now we're animating because we have our data plot here, and we're just replacing this this plot. And after 256 examples, it manages to basically find the decision boundary that we had in mind. So success. And it looks like it's predicting, the color represents sort of how confident it is. And I can see these points here are like a little bit more dark blue. That maybe indicates that the model is sort of not so sure about those ones. But over here, they're sort of quite close to pure cyan, indistinguishable from pure cyan and pure magenta over here, so it looks like it's pretty confident about those ones. I should say you've got to be a little bit careful reading these plots because if we sort of zoom in, actually when we're plotting, you can only choose one Braille character, one color for a whole Braille character. So like all of the points here need to be the same color, and so I'm just mixing the colors with matplotlib, and what that means is that like this one here is obviously not part of the line, but it's being colored white. And actually the points near it are being colored, instead of like white, they're being colored slightly less white to indicate that this was like magenta. But these ones are part of their own Braille character, so you can see them as like slightly darker blue, which is in the color scheme anyway. They're not being influenced by the line. But anyway, yeah, this looks like a success. And I'll show you one more time this animation, because what I also included in the code is kind of coloring a little bit. You can maybe see a little bit of a flash affect some of the points. That's the point that is being drawn at each training step. Remember, each training step is making an update based on one point. And so I'll do it again. You can see it's sort of flashing around. We shuffled the points, so it's going through them in order, but in shuffled order, so it's going through them randomly. Sometimes it's over here, sometimes it's over here. Every time the model is making a classification, and we're making a small change to the model in order to make it more or less like that, to move the line a little bit, each of the parameters, the bias, and the two scalars on the input weights, to make it more close to classifying that example correctly. And when we go through all 256 examples, it then gets all of them correct, which is nice. So there you have it. That is classical perceptron trained with individual sample stochastic gradient descent, and that is also an introduction to jax.random and the tools we have for managing random state with jax.random split, and a couple of the many different functions that are available in the jax.random library. So I think that's all we had in mind to go through today. So it remains to leave you with a challenge before next time. If you want to solidify your working with jax.random, you can look through the documentation to your liking. But one example of something you could do to practice your jax is you could maybe move around these data points and use different instead of multivariate normals, use different functions in the library. But what I have in mind is it would also be interesting to define a different model instead of a perceptron, maybe a multi-layer perceptron, MLP, or like an actual deep neural network that takes the output of this neuron and puts it into the output of another neuron. You shouldn't have to change the code much, just the random initialization and the forward pass, and the same code should basically work, although I'm not sure how this one-step stochastic gradient descent algorithm will work. So you'll have to see about that. And then next time we're going to implement deeper neural networks in future lectures, but this is your chance to try that out for yourself and see if you can figure out how to do it before we see the sort of standard way to do that in JAX. So let's leave it at that. Thanks all, and good luck, and I'll see you next time.